We're going to talk about the weight force or the force due to gravity. Okay, so in our everyday life, we use the term weight incorrectly. Okay, when we think of weight, what do we think of?
How heavy something our body.
Right, yeah, how heavy it is, or in pounds, right? We think of weight in pounds. But weight is realistically how gravity affects a chunk of mass. Okay, so weight is really a force. Okay, and this is how we solve for weight. Using Newton's second law, which was this, F net equals mass times acceleration. We're going to use that same equation now, but apply it to a force that's due to the acceleration due to gravity. So instead of A, we'll use G, okay, which is always equal to, what's G always equal to?
14, just,
Yeah, 9.8. Okay. And the negative tells us downward, but we're going to use that in our overall equation, so you don't have to worry about that too much just yet. Okay. So here, the force due to gravity, which is also called weight, is equal to mass times gravity. This equation you need to have on your equation sheet. We'll use that a lot. So Fg is always m times g. Okay? And as long as we're on the Earth, g is equal to 9.8. Okay? If we're on the moon, g would be equal to something else. Okay, but the force due to gravity, or Fg, is how gravity affects some chunk of mass. Right? So we use the term weight. Realistically, we use it incorrectly. Okay, but in physics, weight and mass mean two very different things. Okay.
Wait, so is that force, gravity, or what? What's
Mm-hmm.
that equation?
Yeah, this is force due to gravity equals mass times gravity. Okay, so Fg would always be equal to mass times 9.8. Yep. And this would be measured, our answer would be in newtons. Okay, so if it would say an object weighs 50 newtons, that means it already took mass times 9.8 for you if it's in newtons. If it say it has a mass of 50 kilograms, then that means it's just m. Okay, does that part make sense?
It's not negative.
You always need to add 9.8?
You always multiply 9.8.
Okay, so if it's in kilograms, you multiply the answer by 9.8?
If it says this object has a mass of 30 kilograms, what's its weight, you would multiply it by 9.8.
Okay.
Yep. And the negative, we're going to put that into our net force equation so we don't have to worry about it here. Okay, I'll show you that in a second. Okay.
Well, wouldn't it, because it's on the ground, wouldn't it, how would it be negative?
Gravity's still pulling us downward. So our force that's due to gravity always pulls us downward toward the center of the earth. All right, you place a watermelon on a spring scale. If the mass of the watermelon is 4 kilograms, what's the reading on the scale? And realistically, like, our scales in the United States read pounds, right? No scales read newtons. But when we ask for what's the weight or what's the reading, we're looking for it in newtons. Okay, we're trying to solve for Fg.
Be like FG 38.5. What do we have to do to get it in newtons, or is it just automatically in newtons?
All we do is take 4 kilograms times 9.8, and that gives us in newtons.
Okay, but I'm saying our base one is kilograms. We're not like, it doesn't need to be.
We don't need to be in grams. No, a newton, the unit for a newton is a kilogram times meters per second squared. Okay, which is mass times acceleration.
Will we ever get those in grams and like up?
Yeah, it's possible.
Meter times what?
Mass times 9.8. Okay, so, oh yeah, this kilogram is a kilogram times meter per second squared. So this is the unit for mass, and this is the unit for acceleration or gravity. Right, so that's where that Newton term comes from. Okay, so that means in order for a Newton to work, you have to have your mass in kilograms, have to have your acceleration in meters per second squared. Okay, so all we're doing to find the weight of our watermelon is taking 9.8 times 4, which is equal to 39.2 newtons. Right, that's it. Okay. So if we had a free body diagram of this, right, here's our watermelon, here's our force due to gravity. Right, that's the only thing that's acting. So we're taking just m times g, and that gives us 39.2. It's a scale, so it's not resting on a surface. You know, at the grocery store, like you have a scale that bounces, you know what I'm talking about? It's hanging. So realistically, we'd have a force like this. Yeah, you would have a tension force. But all we're trying to solve for is...
So you don't have to draw that thing out?
Not when we're solving for just weight. No, I just drew it to show you what it looked like. Okay. Okay. What's the weight of a person that has a mass of 46 kilograms? That's it. This is really as easy as it gets. So don't ever tell people your weight in newtons. It makes you sound a lot heavier than you are. And it read it in newtons. Okay, what was it? 450.8. Okay. And units for weight are newtons. Okay, so listen carefully. If it would ever give you a something that says it weighs this many newtons, that means that they already did this for you, right? You could solve for mass from that. Okay? Okay. We're going to talk about something called apparent weight. Okay? And in this chapter of physics, every physics textbook, every physics class I've ever taken likes to use the example of someone standing on a bathroom scale in an elevator. Okay? Which obviously people do at some point during their day. Okay? So the example is silly, but we're going to look at how it affects your weight. Okay? So a bathroom scale contains spring. The scale exerts an upward force on you, which we usually call the normal force. I don't really like it when it says force of the spring. This is usually the normal force, right? So we're standing on a scale. Gravity's pulling us down. The scale is pushing back up on us, which we'll call the normal force. So this right here is what the scale will read. That's how we solve for these problems when we're dealing with a scale. Okay? So the reading on the scale depends on how much force you are exerting on those springs, because it has to exert that same force back up on you. Okay, so get out your textbook. I want you to read on page 98. This explains apparent weight just a little bit better, or it gives you a little bit more information on apparent weight and these scale problems. Your mass is 75 and you're standing on a bathroom scale in an elevator. Starting from rest, the elevator accelerates upward at 2 meters per second. What's the reading on the scale? So get written down what you need to, and then we'll work this out together. This is like physics, like people's favorite example problems to do. It makes like no sense, but that's just how it goes. I mean, the situation itself makes no sense. The problem makes sense. The situation.
So are we using newtons equal kilograms times?
Yeah, we will. We will. Yeah. Yeah. Let's set up. First thing we should do with all force problems is set up our free body diagram. Okay? First thing, gotta have your free body diagram. How many forces do we have here? Just two, right. Gravity, 2, and normal, okay? And this is really the scale force, right? However you want to label that is fine. I usually always just keep it at the normal force because it's the surface exerting a force upward on you. So this is what we're solving for. Okay? Once we have our free body diagram, we always then go to our net force equation. And we say upward forces minus downward. Okay? So that's going to be the next step in like all of our problems. We draw the free body diagram, we set up our net force equation. What's our upward force here? Just looking at your diagram. Yeah, normal, or the scale force. And what's our downward force? What's the force that's pulling us downward? Gravity. Okay, that's it. That's right. That's right.
Is Fn equal to?
This is just the scale itself. This is what the scale is exerting on us. I'll show you where the acceleration goes. Okay? What do we know that F net is always equal to? Look at your equation sheet. What did you write down? Good. So we're going to just substitute. If we know that F net is equal to mass times acceleration, we're just going to substitute that in right there. Okay? We're solving for the normal force, so we leave that alone. What do we know Fg is always equal to? Mass times 9.8. Now look, right, we said Fg is equal to mass times 9.8. The negative goes right here. Since we're subtracting out forces that are going downward, that's where our negative goes. Don't have to put it in there twice. So here's the difference. We have a total acceleration of our whole system, and we have the acceleration due to gravity. So the acceleration of our system is positive 2. So we're going to start taking 75, which is our mass, times 2, equals our normal force, minus 75 times 9.8.
Negative 580.
Wait, so are we trying to find F in?
That's right. That's right. Whenever it asks what the scale reads, right, this is what we're trying to find, that upward force that the scale is exerting on us.
I like the other ones that are multiplied.
Sorry.
It's okay. I think just differently.
Do we at least see where all these numbers came from, or not so much?
Yeah.
Kinda? Okay. You could always solve for Fg first, right? Take 75 times 9.8 first, and then just plug in the number where it goes here. You don't have to do variables first. You could just solve for it first and then plug it in. It doesn't make a difference. Okay, here we're going to add that 735 over. And we get a normal force of 885 newtons. So, since our elevator is accelerating upward, is this normal force or this scale reading greater than or less than what it would be if it was at rest? Should be greater than, and is it? Yeah, if it was at rest, Fg would equal Fn. So if it was at rest, our normal force would have only been 735. But since it's accelerating upward, we're adding that extra mass times acceleration to give us our actual normal force or our scale reading. Okay, does that part make sense? Are we getting there? Okay, it's all right. We will. Okay. Same situation. What would this reading be if the elevator were accelerating downward at 2 meters per second this time? Okay, it should be less than our equilibrium weight. Okay, so let's solve what that would look like. Does our free body diagram look the same? Yes, it does. Our free body diagram still looks the same. That's right. That's right. So where we set up our net force equation, normal minus gravitational. Here we know this is mass times acceleration. Mass times gravity. And you're right. So instead of putting a positive 2, whenever it says it accelerates downward, that means we're looking at negative 2. Your mass. Okay, this is a little simpler than the problem we just did. Okay, it says we weigh this many newtons. So what does that mean this force is equal to? Yeah, that means this is Fg, 585 newtons. Okay, and we know that Fg is mass times 9.8. So to find our mass, all we're doing is dividing by 9.8. That's literally it. Okay, if it's in newtons and we want kilograms, we divide by 9.8.
Is mass always in kilograms?
That's right. Okay, that's it. Okay, whenever it says it weighs this, if it's in newtons, they already took it times 9.8 for you. Okay. What would the scale read if we were on the moon, not on the earth? Try that one. Okay, if we were on the moon, which has an acceleration due to gravity of 1.6, when we go to the moon, will our mass change? No, but our weight does because we're not on Earth. So if I was going to find the scale or my weight on the moon, no. We're going to take our mass that we just solved for, and we take it times 1.6 to get it back into newtons. Right? If we know that our mass is equal to 59.7 kilograms. It doesn't change when we go to the moon, but our weight, or our Fg, does. Okay, so we take 59.7 times 1.6. Griffin, what'd you get? Mm-hmm. Okay, so on the moon, it appears as though we weigh a lot less. Okay, but realistically, our mass didn't change. Gravity just affects us much less on the moon than it does on the Earth.
I got it.
Okay.
My son's
Okay, so just think about this second question that's listed here. Which would reach terminal velocity faster? A heavy object that's compact or a light object that has a large surface area? How many of you think the first option, heavy and compact? They would hit the ground at the same time in a perfect world. Not if they don't have the same shape, sorry. Remember we watched that video, the mass of it doesn't matter, but the shape of it does. What do you think? Which would reach terminal velocity faster? Which of these would have a greater, which of these would air resistance affect more? Lighter with large surface area. So if I drop two things, right, if the shape of them are the same, they'll reach the ground at the same time. That's what his experiment showed us. That these balls don't weigh the same, but they have the same shape. They'll reach the ground at the same time. If air resistance affects one more than the other, then it'll slow it down. So terminal velocity is when that light object with large surface area is affected by air resistance so much that it's no longer speeding up as it falls toward the ground. It's just kind of getting there at constant velocity, right?
You use a cannonball and like a rubber ball or something?
In the Galileo experiment, yeah, he used like a steel one and like a wood one. Mm-hmm. Okay. Let's try this one. Okay, get written down what you need to here.
diagram for it, that's what help us do.
The diagram helps us see what are our positive forces and what are our negative forces.
What if you messed the diagram up? Does that just ruin the whole problem?
It's possible, yeah.
Oh my god, I'm just terrible.
So now.
You can do it.
We need to do
What's the only two forces we have acting here?
gravity and tension.
Yeah, gravity and tension. Right? It's being pulled by a rope or a cable, and gravity's pulling it downward. Okay, so we're helping repair. If a rope is used to lift materials, it's guaranteed not to break as long as the tension doesn't exceed 450. You fill the bucket until it has a mass of 42. What's the greatest acceleration that workers can give the bucket as they pull it to the top? Okay, so if you have a heavy object and you pull too fast, what could happen to the rope? Our net force upwards minus downward. Okay? That's the two steps that hopefully you are getting kind of on your own. We draw the diagram and then we draw our net force equation. Okay? It tells us here that our tension cannot exceed 450. So we're trying to find the maximum acceleration to match the maximum tension. So we're going to go ahead and plug in 450 newtons here. Okay, as our tension force. Because we want to see if our tension reaches 450, what's the biggest acceleration that we can have. Okay? What do we know that force due to gravity is always equal to? Not just 9.8. No. Mass times 9.8. And the negative goes right here. Okay, since we're subtracting a downward force, that's where the negative goes. Okay, what do we know that F net is always equal to?
42 times acceleration.
Good, 42 times acceleration, which is what we're solving for. We're solving for the acceleration of the whole system. Okay, so we have all of our numbers plugged in. Do we see where those numbers came from? Yes or no?
Yeah.
Okay, so let's go ahead and solve.
So do we just substitute, like FT for FN?
Yeah, so since it's not on a surface, we don't have a normal force, so the only upward force we have acting is the tension force.
Who's not ready with this force, is it?
I think I'm pretty messed
50-kilogram bucket is being lifted by a rope. The rope will not break if the tension is 525 or less. The bucket started at rest after being lifted 3 meters. It's moving 3 meters per second. Acceleration is constant. And is the rope in danger of breaking?
There's a velocity pattern.
Yeah, it does. So this one, you might have to use your kinematics to solve for the acceleration of our system.
Oh my god, we should kinematics in this too.
Kinematics goes for like every chapter, man.
Yeah.
It's peaked at 21 millions total.
Did you see that they were the biggest underdog in modern television switch history?
So if we set up our net force equation, we'd see F net equals tension minus gravity. So here's what we're looking at here. We have to solve for the acceleration of our system. We know that it's going to be lifted 3 meters. It's moving 3 meters per second at that point. And we know the rope can only withstand 525 newtons of tension. So this is what we're going to have to do. We're going to solve for acceleration first, okay, using a kinematics equation, because we know mass times acceleration equals tension times mass times gravity. Okay, we're going to solve for acceleration. We know gravity. We know our mass. We're going to solve for what's the maximum tension that could be, it could last using this acceleration we solve for, and then we'll check it. Is it greater than or less than 525? So we're going to see, using this scenario, what's the tension exerted on that rope, and then we're going to see, is it greater than or less than 525?
And that's how much?
Okay, and then we'll say, if it's greater than 525, then it's going to break, right? If it's less than 525, we're good to go. Okay, so using our kinematics equations, I know it's been a little bit. Okay, our distance final is 3. Our velocity initial is 0. Our velocity final is 3.
We're solving for which one?
Right now we're solving for the total acceleration of the whole system.
Wait, how are DF and okay, well, I missed it.
So if you're looking here, DI is really 3 also. DI is also 0. My bad. Okay, so we probably want to use our third kinematics equation here. Oops, sorry, you can't see what I wrote. So that means our acceleration of the whole system is 1.5 meters per second squared. Do we agree with that? Okay, are we on the same page with how we got there?
No.
Or did I do something wrong?
A equals what?
9 divided by 6?
1.5.
No. Divide by 6, divide by 6. 9 over 6 is 1.5. Right? Am I doing it right? Okay.
Yeah.
Okay. So now, this is the acceleration of our whole system. We'll sub in 50 times 1.5, right? Because it's being lifted upward, so it's a positive. We'll see what tension that can withstand. Sorry, it says 565.
Not every problem will be
Any force is measured in newtons.
okay. So the answer is always newtons.
Anytime you're solving for force, yes. Our answer is newtons. So if using this acceleration of our system, right, this situation, they accelerated with a 1.5 meters per second acceleration, is our rope going to break or is it going to last? It's going to break, right? This situation needed 565 newtons worth of tension, and the rope can only withstand 525, which means it's going to break. So yes. Yeah.
What's the difference between this problem and the last one?
Why isn't there always normal force?
Normal force is the force exerted by a surface on an object. So if an object's not sitting on a surface, that means there's no normal force. So like in these ones where it was held by a rope, it's not on the surface, it's in the air. So that means that just tension is holding it up.
It's just like the force from below it. Is that what it means? Ooh, wow.
Oof. Okay, for our second scenario, what's happening to the box? Stay with me, please. What's happening to the box in our second scenario? It's lifting it up. Is our box leaving the table at all? No. So our free body diagram would look like this: normal force plus our lifting force and our gravitational force. That's what our free body diagram looks like. When we have two upward forces, we put them one on top of the other. Okay, so we're lifting with a force of 50 newtons. Our normal force is also pulling us up. So that's what our free body diagram would look like. Okay, we're lifting. We still have a normal force because it's not leaving the table. And we have our gravitational force. Okay, so F net in this case would be equal to what? Yeah. Right, the normal force plus the lifting force minus gravity.
Is it always going to give us the lifting force? I'm not seeing lifting force on here.
This is just like an applied force. You could call it applied too. Okay. I don't know if that's on that sheet or not, but okay, that's just any force that is like a contact force. So anytime we push or pull on something, we're touching an object, that can be an applied force. Okay.
Have we used the F thrust at all?
No.
How often are we going to use like the spring?
Okay, is our box accelerating in the vertical direction?
Yes.
Mm-hmm.
No.
It's not leaving the table. Okay, so I want you to go ahead and solve here for the normal force. I want you to solve for the normal force.
When you pick it up though?
He's attempting to lift it, so he's going like this. Right, but it's not leaving the table.
So technically,
You still have a normal force.
the weight is less.
That's right.
But the mass is the same.
That's right. Solve here for the normal force. All right, I even gave you the numbers. It lifted it with 50 newtons. Our gravitational force is 10 times 9.8.
So they're all equal to 0.
Yep, because our box is not leaving the table. It's not accelerating in the vertical direction.
So then why, when it's hanging there, it's not moving either?
That's where our net force is equal to 0 in those moments. Oh, no. When it was hanging, the whole thing was moving up and down. Like I said, it was lifted, whatever.
But if it's just hanging there,
If it's suspended,
it's still equal to 0.
that's right.
Interesting. So we're so
Subtraction got how like
I did it on paper.
48 newtons.
it'll get you.
Okay.
It was less than
normal.
Which does it make sense that it's less than our normal force at equilibrium?
It has to be.
It does make sense, right? Because we're lifting, we're taking some pressure off the normal force. Go ahead and solve for the last one then. Okay, you do the last one on your own. This time, we're pushing downward on it with 50 newtons.
Is there a certain point where it'd be like, with this amount, it would actually get
Yeah, so
lifted up?
if your lifting force is greater than 98 newtons, right, it would leave the table to be
Or
greater.
if it was greater than whichever one we find, it would go through the table?
Well, yeah.
So what F gravity is going to be 50.
Theoretically.
F gravity is 50.
No. Gravity is still always mass times 9.8. The pushing force is 50. So how many upward forces do we have on this third example? One. And how many downward forces do we have?
2.
2. Good.
So we draw it the same way but opposite.
FL.
Yeah, so our FL goes on our FG side.
What is FL?
Yeah, well, or F push. You can call it whatever you want. You can call it F applied. You can call it FP for F push. It literally doesn't matter.
Will we do anything to like?
I'm gonna
I don't have one.
Like,
Doesn't affect gravity at all.
like breaking, are we gonna like, I don't know how to
Can we try to
say
push
it.
a box?
So like,
No.
if you have a wood and we're trying to break it, you have to use a certain amount of force. But if you're using a wedge, like an axe, would you need to use the same amount of force, or would you need to use less? Because you're hitting it with less surface area as like a hammer.
Yeah, it gives a more defined breaking point. I don't know the answer to that.
So we're not gonna do it.
Well, yeah, I don't know the answer to that. No, we don't deal with that kind of stuff. Sorry.
You know what I like is those.
I was just wondering if because it would be different. Hydraulic presses.
Yeah, I don't know that. Yeah, those are freaky. No, we're not going to get one of those. Okay. If we ever get a negative normal force, something went wrong. Right? If you have a negative normal force, that can't happen. Normal force is always pushing up on our object. So if you get a negative normal force, that means that our object is no longer sitting on our surface, which means it doesn't have a normal force anymore. Okay, so if our lifting force here would have been 150 newtons, that would have caused it to leave the table, which means we would have had no normal force anymore. Okay?